reactions which we try to check, you can see that most of them are excluded at around 1 TeV mass. The next one is the same thing for Atlas. And of course, the Atlas and CMS results are always very similar to each other. And also CMS, we search for other exotica, for the alternative models. And here we also exclude below 1 TeV mass all these phenomena. But for instance, the compositeness excluded below 10 TeV masses. So the conclusion is that broken symmetries play a fundamental role in particle physics. At LHC we found the standard model Higgs boson, and it doesn't look like a Higgs boson of any other model, unfortunately. Since 2015, the LHC collides protons at 13 TeV, and let us hope that we find some deviation from the standard model. The simplest SUSY models do not seem to be supported by experimental data, so we developed simplified approaches. Simply look for phenomena which are different from the standard model. So far we couldn't find any. And once we find some, we try to interpret it using the supersymmetry. And the final is adjust theory to data and not the other way around. Thank you for your attention.
Thank you very much for this nice summary about symmetries and the legacy of Wigner in these days, after so many years, that we really depend on the...
This is for the room, that is for the record.
So let me call the next speaker, and I would like to invite David Laschke from the University of Wrocław.
This is the, and this is the remote control.
How we can think about neutron stars following Wigner's ideas.
Okay. Is it working? Okay. Good. Thank you very much. I feel very much honored to have received this invitation to talk here in the Academy. And of course, it's also a big pleasure. And I'm reminded of WIGNER115 in this room. And I would like to revive the spirit of this great meeting. Okay, yes. So, I was asked to even address modern observations.
It's not what I gave you, it's not.
No? Ah, yes.
We better turn it off.
Yes, you turned it off, huh?
Yes.
Okay. Oh, now it's fully operative. So I got the task to relate Wigner's work with neutron stars. And I picked two aspects. Of course, the aspect of symmetry, which is essential not only for the elementary particle physics, but also for the physics of dense matter. When we speak about the dynamical symmetry breaking, and its restoration under extreme conditions. Extreme conditions like we find them in the interiors of neutron stars, for instance. But we find them also in heavy ion collisions, where we explore the QCD phase diagram. I will talk a little bit about this aspect, but then mainly focus on the recent measurements of gravitational waves from neutron star mergers and what perspectives this gives for the investigations of symmetry restoration in superdense matter. Finally, you all know the bright Wigner distribution. It plays an important role when we speak about thermodynamics of unstable particles also. And here I will show you then a little recent work related also to the approach for conserving approximations, which results in a squared bright Wigner. And I think this is a good point then to stop. I took from the recent NUPEC long-range plan in nuclear physics this phase diagram of quantum chromodynamics. It has three axes: the temperature, the baryochemical potential, and the isospin chemical potential. And isospin plays a big role when we would like to speak about astrophysics, because neutron stars, as the name says, have broken isospin symmetry. We have predominantly neutrons, whereas in heavy ion collisions and in large nuclei, we basically probe symmetric nuclear matter. Neutrons and protons come in about the same number. In this long-range plan recent phase diagram, you see a lot of lines. You see not only the line, which is of course an artistic line at the moment, which separates the hadronic world, this rosé region, from the world of quarks and gluons, the quark-gluon plasma. You see here a critical endpoint of first-order phase transitions, which we search now in heavy ion collisions, for instance, at LHC, at RIG, and at the SPS at CERN, but also in future experiments, which are particularly designed to probe this denser region of the phase diagram, NICA in Dubna and SES experiments at FAIR Darmstadt. Here we try to recreate matter which is more similar to what we find in astrophysics in the collapse and explosion of compact stars and supernova explosions, but also in the neutron star merger events, which are already to be found here in this NUPEC long-range plan. Here we see one of the possibilities how the phase diagram could look like, that a first-order phase transition should then extend down to temperature equals 0, and actually also in the isospin asymmetric region, which is probed by neutron stars. So it will be essential what we find in neutron star interiors. Is there a strong first-order phase transition or not? When we will find it, then we have good reason to believe that there should be indeed this critical endpoint of first-order transitions, because lattice QCD simulations on the temperature axis tell us that the phase transition over there is crossover. So somewhere here must then be the endpoint. However, based on symmetries, now we come to Wigner, based on symmetries, authors have suggested that there might be a second endpoint. Story might be different. So here is the endpoint which we have just discussed, but it might end here and down at temperature equals 0, which we probe in neutron star interiors. There could be also a crossover based on the argument that we have similar symmetries in the hadronic world and in the quark matter, quark-gluon matter. So where gluons form an octet, similar to the octet of vector mesons in hadronic world, quarks can be versions of baryons, and Goldstone bosons of broken symmetries like chiral symmetry have their analog in the pseudoscalar mesons, predominantly the pion and the kaon, which are well known. So it could look also like this. So really, we need to make the experiment, and therefore what we have witnessed in the news recently, the measurement of neutron star merger event, is so important to tell us more about the physics here in the region of very low temperatures and high densities, which we cannot explore in heavy ion collisions. In heavy ion collisions, necessarily, we have a lot of entropy and heat, and if we are lucky, we will be able to probe this critical endpoint in heavy ion collisions. Yeah, so how does a neutron star look like? So this is a toolbox for nuclear physics from the outer crust, where we have a lattice actually of nuclei, and so here, outer crust, the lattice of nuclei. Then when we come to the more denser interiors, these nuclei get modified. They might actually become, get different shapes. These shapes, like ellipsoidal shapes, might merge to cylindrical shapes. They might merge then to plates, and these might again merge, and then we will have a mirror symmetry here, where in the interior of the nuclei we have dense matter, and here we have a homogeneous phase of dense matter and no clusters, no structures anymore. And these structures, this phase transition, including structures with surface tension, and so this is also called pasta phase. So this is a pasta phase transition. When we come then to this border, this is this border here of the nuclear matter, no, nuclear structures to infinite nuclear matter. This nuclear matter is predominantly composed of neutrons, so we have here neutron vortices also, because this is probably superfluid neutron matter. And finally, when we come to the very core of a neutron star, the density exceeds probably the critical densities of normal nucleonic dense matter, and exotic forms of matter can be formed. And here is a sketch taken from a textbook by Fridolin Weber. This is only an approximate idea how many possible alternatives we have for the neutron star interior. And I will focus a bit on this part of this cake, where we speak of quark matter in different superconducting phases. And the question, is this a first order transition, or is this a continuous crossover transition, will be essential here. So let us now come to the observations. Neutron star interiors may have a strong phase transition or not. This is what we would like to ask. And here it is essential that we have ideas about the equation of state in neutron stars. The equation of state is directly reflected by the systematics of masses and radii of compact stars. And when we would be able to measure simultaneously masses and radii of a whole set of neutron stars, we could, by this way, from observations, reconstruct the dense matter equation of state. This could give us a similar benchmark as we have from lattice QCD simulations on the temperature axis. Therefore, this is very important, and this importance has been recognized, and there are many experiments, observations, satellite experiments going on to constrain masses and radii. So far, we have separate measurements of masses which have reached a high level of precision. Like, for instance, for these two examples of high mass pulsars, these are the examples of pulsars with the highest precisely measured masses. Here, 2.01 solar masses, and slightly below 2 solar masses for this object. Now the question is, these two objects which we have just seen, what is their radius? We don't know yet. It could be that these two objects have very different radii. What would this tell us? This would tell us that due to the specifics of dense matter, they could be mass twins, so having same mass but different radii, as solutions of the Tolman-Oppenheimer-Volkoff equations, which govern the hydrodynamic stability of such objects. We can have one, let's say, boring solution. The interior is composed just of stiff nuclear matter. The other solution is a more compact solution, where in the interior we have a new form of matter, let's say quark matter. And the phase transition is governed by a large latent heat, so there's a large effect of compactification, because the density, the typical density where the quark matter lives, is much higher than the one for the normal nuclear matter. And so the mass radius characteristics might look like this. So we might have here a typical hadronic branch of compact stars, let's say up to 2 solar masses. Then a phase transition in the interior sets in, and it comes to this restructuring of the interior, as a result of which, through an instability, so here we have these little dashed lines or dotted lines, we reach a new stable branch of compact stars, which have in their interior then a core of quark matter. And they are separated by the normal second family of neutron stars, and therefore they form a new family, which is called the third family. The first family are white dwarfs. They are far away at much larger radii. And okay. So here is a schematic view of how we have to imagine this one-to-one